is a list of all bit strings of length n. Ben yukarı çıkıp üstüne bir şey alıp geliyorum. Bu gibi altı gelmedi. Kadetten açık oldu. Bu konuşan bir geldim oraya. Gelmedi tekrar. Okay. So we output a list of all bit strings of length n. Sesim açık değil mi normal derste? Okay. All bit strings of length n. Okay, the base case is first, if n is 1. N is 1 means that I have one positive integer. This is 1. So the only possibility is 1, right? There's only one positive integer. So make list L1. So there's only one bit, so it might be either 0 or 1, okay? So in which case, there is only one bit difference, and we're done. It's already conforms to the binary reflected gray code, okay? There's only one bit difference. So make list L1 containing, make list L, sorry, L containing bit strings 0 and 1 in this order, else generate list L1 of bit strings of size n minus 1. This is minus n minus 1 by calling BRGC n minus 1. Okay, so we make a list L containing bit strings 0 and 1, and that's what we do in this case. Okay, in that case. Here, we generate a list of bit strings of size n minus 1 by calling BRGC n minus 1. So we generate, we call this function recursively to form two lists that conform, one list that is one less than size. Okay, if we're talking about 4-bit strings, it means we first generate 3-bit strings that are according to the binary reflected gray code, okay? And then we add 0 in front of each bit string in L1, add 1 in front of each bit string in L2, okay? 2-bit strings generate, sorry. Here, we do another operation. Copy list L1 to list L2 in reverse order. Okay? So we first generate a bit string. If it's 3-bit strings, 8 of them. Okay? That is L1. And then we have L2, which is the reverse order of these bit strings. Okay? And then we add 0 in front of each bit string here. And then we add 1 in front of each bit string here. So what happens here? Because it's all zeros in the beginning, okay? Let me finish this and then I will explain. Append L2 to L1 to get list L, okay? So we are trying to obtain n-bit strings that are according to this 1-bit difference property. So first we generate a bit string that is of n minus 1 length n minus 1, okay? So if this is n minus 1, and this is according to the binary reflected gray code property because it's we obtained it by calling it the same thing recursively, okay? So now in here, in this list, this is only, the difference is not in these 0 bits, right? When we appended them. The difference is somewhere in the remaining n minus 1 bits, and that is ensured by the binary reflected gray code property, by the recursive operation, okay? There is only 1-bit difference here up until this point, okay? And here, because it was the reverse order, now this bit string, the last one here, this bit string, and this bit string of length n minus 1, both of them are the same, okay? Because we copied list L1 to list L2 in reverse order. The same list, we just copied it in reverse order in the second operation, which I forgot and then I added here, okay? In the second step. So this is basically the same bit string of n minus 1, but in reverse order, okay? The second list L2. And so the difference here is only in this bit. 0 becomes 1, okay? Because this is the last of this list and this is the first of this list, because this was in reverse order. So from here onwards, the difference is not in the first bits 1, okay? But this is ensured by the binary reflected gray code property of this within here, okay? This 1-bit difference, okay? So from here to here, I have ensured that there is a 1-bit difference between two consecutive bit strings, okay, with this algorithm. Now I need to make sure that the first one of this and the last one of this are of 1 bit difference. And is this true? Because list L2 was the reverse order of list L1. The first one here is actually the last one here, okay, in the n-1 portion, length n-1 portion. So the only 1 bit difference is this 0 and this 1, okay? So there is also a binary reflected gray code property. Let's go over the algorithm. We generate a bit string of length n-1. Remember, we're in the decrease and conquer case, so we solved it recursively, the n case, by calling it the n-1 case. We generate a list, and then we copy this list to another list in reverse order, okay? So we have 2 lists. The second one is in the reverse, the 2-bit strings of each with length n-1 and each in binary reflected gray code property. But the second bit string is in the reverse order with the first bit string, okay? And we add 0 in front of each bit string of the first one, and then we add 1 in front of each bit string of the second one list, okay? And this ensures we just check that this ensures to the binary reflected gray code property. So for instance, with n equals 3, for instance, let's check. We will call n equals 2, which will in turn call n equals 1, and that will make 0 and 1, okay? And then we generated a list. We copied the list, but this time in reverse order. So this will be 1, 0. And then I add zeros here, ones here, okay? And this is for n2, okay? Remember, just check that there's just a 1 bit difference, and there's a circular property also, okay? For n equals 2. For n equals 3, what did I do? I already made n equals 2. Now I will take this. So this is now my list L1. The list L2, it will be in reverse order, 0, 1, 0, 0, okay? List L2. I will add zeros here and ones here. And this will be a binary reflected gray code property, okay? Just check that there's a 1 bit difference between each 2 consecutive bit strings here, okay? 1, 0, 1, 1, 0. And also between the last one and the first one, there's a 1 bit difference. This is ensured by this algorithm, which is a decrease by 1 conquer, decrease and conquer algorithm, okay? Note that bu arada ben kayıt almadım galiba. Kayda başlayan var mı? Tamam, güzel. Note that BRGC is cyclic. I mean, it has to be because the binary reflected gray code property is a cyclic property. Okay, so that was the examples we had for the decrease by 1. Now we will continue by decrease by a constant factor algorithms. Okay. Now I will introduce another problem called fake coin problem. And you will think about a decrease by a constant factor algorithms. Remember when we said decrease by 1 algorithms, we were talking about how to solve the problem for an input of size n by using a recursively calling the same algorithm for an input of size n-1, okay? That was decreased by 1, n to n-1. When we say decrease by a constant factor, factor is like if I have an input of size n, I could recursively call inputs of size n over 2 maybe, or n over 3, n over something, okay? And that something is the constant, okay? And then because we factor it, we divide it, okay? So the fake coin problem is this. Among n identical looking coins, one is fake. Okay. So we can say that with weight-wise, okay? I mean, think of them as gold or I don't know, something like that. Its weight is supposed to be like 1 kilogram. You could think of it as coins, but it would make more sense. Like, remember the balance scales that was used in the markets in the past? You would put like 1 kilogram something, and then in the other ones, in the old times, I don't know. You're not that old enough, but you probably know what I'm talking about. So that's I mean, it looks like a 1 kilogram, but it's not. Okay, one of them. Like, think of them as all 1 kilogram. No, one, I don't know, maybe 100 grams or something like that. But one of them is lighter than that or heavier than that. I don't know. But only one of them is fake, and all the others. But you don't know which one. So among n identical looking coins, one is fake. With a balance scale, and with balance scale, this exactly means, and how can I have a balance scale. I have like, I don't know, 100 grams of these, I don't know, beans or something like that. What, I don't remember what it's called. I mean, even in Turkish, I don't remember what it's called. How would you find the fake one? The exact same fake one. Actually, this was also used to check diseases, I think, in the wars, in the armies. I think one of them, or which ones are positive for some disease. They were using a similar idea, but I don't remember it exactly. How would you find the fake one? Let's say I have like 8 of them, and one of them is not true. And you have a balance scale. How would you find the fake one? From the online class, any ideas? No ideas? Okay, let's say I have 4 coins and one of them is fake. One of them is fake, and I have a balance scale. I just drew it like that. This is A, B, C, D, and they are supposed to have the equal weight, but one of them is different, but I can't differentiate which one visually. So I have to check. I don't want to check each one of them. I mean, the exhaustive search approach would be what? What would be the exhaustive search approach?
Factor of 4.
Factor of what?
4.
No, I'm not talking about complexity. I'm just asking, if I wanted to do it with exhaustive search, how would I do it? I have only 4, and I know that one of them is fake, but I don't know which one is fake, and I want to find it out.
Well, we simply pick one randomly.
Pick one randomly, but what will I do that? I already have the answer from the class, but I want to learn what your idea is.
Pick one from the
Okay, I
deck,
picked
and
A. And
we look its weight.
you look its weight how? I have a balance scale. I have to put something else here too. I mean, I couldn't draw it properly, but okay, I
We
have
need to
to put
pick
something.
different.
Sorry?
We need to pick another one also.
Pick another one. That's what your friend was saying. Let's say B. I check A and B. If they are the same, then none of them is fake. Okay? So I can check all of these pairs, right? Of 2 for choose 2 pairs. But what if I don't want to do this? I want a more efficient thing. Instead of can you think of something like binary search, like what? I mean, what's the exact? The idea is similar to binary search, but yes. Uh-huh. Okay. If they are different, yes. Let's say one of them is higher. Okay. In there. Okay. So and then I factored it out. I divided the options by 2, possible size. Now I need to check C and D, right? And check which one is the fake one in this group. That's what we would do. Same thing for 8 also. Now I would divide it into 2, 4 and 4, and then check which one the fake one is there, and then find it. Okay. I think they were doing it in armies when there were like epidemics. I don't remember the exact method, but they just simply didn't have the resources to test each of them. Okay. They would divide the soldiers into some groups and check them randomly, and then if there is a disease in one of them and then they checked it, something like that, they would do it. But I don't remember it exactly. If I need to check it again, but it was not like randomly, or I don't remember, but it was a similar idea to this. Okay. So with a balance scale, I'm continuing from here. Gelebilirsin. We can compare any 2 sets of coins. Okay. Divide n coins into 2 piles of coins each. Of course, if this is not a power of 2, then there might be a problem. I mean, it's if I have odd number of coins at any given point, then I could do what? I could put, like, let's say I have 9. I could put 4 of them in one, 5 of them in one, or I can check one of them out and check whether the remaining 4 and 4 is, if they are equal, then that one is the fake one. If they are not equal, then it's among one of these 2 parts. Okay, you can modify the algorithm for the odd case. So it's not, and may not, it doesn't have to be a power of 2, but you need to, the one that I just described is according to the power of 2, but it can be modified for other purposes. So 2 piles of n over 2 coins each. Leaving 1 extra coin aside if n is odd. Okay. So the resulting recursion formula is Wn W floor of n over 2. That's why we say floor of n over 2 for n greater than 1. And W1 is 0 because if I have 1 coin and if I know that one is fake, then that one is fake. Okay, I don't have to make any computations at all. So this is the same recursive formula for binary search. This recursion, I mean, it's not exactly like, it's very, but it's more like binary search really. This recursion is identical to the one for Of course, the worst case comparison, it's identical because I always do this. So the worst case. Now I always reach to the worst case because I have to find that one particular point and that has to be somewhere in the end. So it's exactly like the binary worst case of binary search each time. Identical to the for the worst case number of comparisons in binary search. Actually, the interesting is here is that if instead of dividing it into two, I divided them into three, would it be better? Correct answer, but why? So I have I put them into three piles of each approximately n/3 each. And then I check two piles. One pile would be different from one of the other piles. So I have to check all the three groups one by one as pairs. Hadi Türkçe söyle ama why it's efficient? Nasıl yapıldığını herhalde çok kişi tahmin eder değil mi? Aynı operasyonu 3 pile için yapacağız. Ama constant faktörler bizim için önemli olmaması gerekmiyor mu? O zaman 4'e bölerim daha iyi olur. 5'e bölerim. 5'e bölersem?
Tanesini karşılaştırabildiğimiz için.
Ha.
O yüzden bölünce ikili aynı şey bekliyor.
İkili aynı şey. Peki 5 olsa? O zaman
3 tane kalmış oluyor.
ha, anladım. Ama mesela 3'e böldüğümde diyelim 2 taneyi aldım. İkisi eşit çıktıysa o zaman kesinlikle bu tek file'dı. Onu biliyorum. 2 taneyi birden atabiliyorum diyorsun. Informal bir açıklama olarak olabilir, evet. That would be your ungraded homework to think about. Maybe your friend understood it, but I don't think that the rest of the class is convinced. Paylaşmayı tekrar yapmam lazım galiba. So the interesting point here is that biraz geç algılıyor. Yeşil kırmızı karıştı. Daha yeni kırmızı oldu. So it will be your ungraded homework, okay? Now let's continue with, if this is clear, I will continue with a very, I think I find it really interesting, of a multiplication technique that is based on this idea. It is called Russian peasant multiplication. Peasant means villager. Russian peasant multiplication. So now I will first give some history, math history, according to Western visitors. This method was used widely. Hesap makineleri yok tabii, of course, they don't have calculators. And they have to make calculations all the time. In the 19th century. In fact, this method was known to Egyptian mathematicians. As early as 1650 BC. BC'den bahsediyoruz arkadaşlar. Milattan önceden yani. 1650. Şimdiki 1650 yılı bile değil. Bana hani öyle teoremler şeyler düşünmüşler ki eski Yunan'da. It always looks amazing to me, the level of sophistication of thinking so many years ago. Yani evolution nedeniyle daha advanced olduğumuzu zannediyoruz ama çok emin olamıyorum gerçekten. Bazı şeyler hala o zamanki hani ispatlanamamış şeyler var, o zaman düşünülmüş. Bizim için neden önemli? Why it is important to us? We will see, we will discuss about it after I mention you the algorithm. Okay? Because when you think about the algorithm, also keep it aside that why it is important to us in nowadays on computers. It might be important. Okay? So we have, it's basically multiplication of two integers, two large integers, but imagine the times where they did not have any calculators and they have to do this on, I don't know, paper, or I don't know what they were using at that time. But even there, they needed some fast mechanisms to do it, okay? So they came up with this. It probably dates back to the Egyptians. O İskenderiye kütüphanesi gitmeseydi, İnsanlık nerelerde olurdu? N and M are positive integers, okay? There is a the recursive formula, it's a recursive method, is this, okay? If N is even, okay, one of them is even. I don't care about the other one. The other one might be even or might not be even. I fix one of them. I say that this is N, and I only look at N, but I cannot keep changing N and M because I could be doing the same things, the reverse things in the meantime. If N is even, is this true that N times M is equal to N over 2 times 2M, right? Divide one of them into 2, multiply the second one. And I multiply these two numbers now instead of multiplying N times M, okay? If N is odd, I say that N times M is equal to N minus 1 over 2 times 2M plus M. Okay? And I keep doing this recursively until I reach the point where N is 1. In which case the rest would be, but there's the odd cases that I need to save somewhere, okay? So because if it's a power of 2, N is a power of 2, then it's not. I will solve an example, but yes, you can ask still.
N can be also N.
No. I have two integers, okay? Let's say, I don't know, 892 and 1600 something, okay? I say that, okay, this one is N, then the other is M. And in all the iterations, the same one is N. That it's 682 is N, then it's always that part. Of course, when I divide it into 2, it becomes something else, but that is still N, okay? Let me solve it in yes, that's my, it might be even in the beginning, but when I divide it into 2, then it's not, it's odd now maybe, okay, then I may fall into the odd case and do it like that. But then I solve it the odd case, now it may become even again, okay? Or odd stayed odd, it all depends. This way, I will solve it in an example. We can compare n times m either recursively or iteratively. So let me solve it in an example, then I think it will be crystal clear. So n and m, okay? Let's say my n is 70, m is 85 in the beginning, okay? In the column. So I want to multiply them. So how do I do that? I divide this into 2, 35. I multiply this by 2, 170, okay? This is the method. You may think that, okay, why I could have multiplied the two of them. It would be simpler, but this is just the method that was used. 35 and 170, okay? Because n is even now, it's in the n even case. Now n became this part odd, okay? It's 35. So when I divide it into 2, and so I'm in this case, I have to look at n minus 1 over 2, okay? And minus 1 over 2 is 34 over 2, 17. 2m is 340, but now I have this plus m, okay, which is 170. Okay, I have to keep it here, save it somewhere, because I need it at the very end. Okay, if everything is clear, I'm going on. Now, can I divide it into 2? I'm again in the odd case, so it becomes 8, okay, and this becomes 680. But because I'm in the odd case, this becomes like 340 now. Plus m, because, okay? And this was m here. Okay? Daha bitecek ama daha bitmedi. 1'e kadar gelmem lazım en kısmında. Ama evet, at any given step bu yani. Hepsini toplamam lazım şunların ama. 170 artı 340 artı 688'in çarpımı. Ama 688'in çarpımı ne onu bilmiyorum. Devam edeceğim oradan. Tamam? And at any given step that's true. But I have to keep going on until n is 1. So I divide, now it's a power of 2. It will all be even in the subsequent stages. So it will be 4. And this will be 1360, right? So I will divide this into 2, and this will be 2720. Okay, I multiplied it, but I don't have any remaining parts now because we're not in the odd case. Now it will be 1 times this 540. Okay, but I had these also here. This is where I reached the end. Okay, now I sum up 540, 170, and 340, and that will give me my result, right? Because I had these extras here. Now it's 5,440 plus these. And this is what? 5. Okay, that's the result. Add all elements in the M column that have an odd number in the N column. And that is the Russian peasant multiplication, to multiply two large integers. Why would it be important to us in computers? Remember, multiplication is an expensive operation in computers. So instead of, if we implement this method instead, we could implement this in computers for multiplication, but why would it be important? What am I doing here basically in each step? In each step, what am I doing? I divide it by what? 2 and multiply it by 2. And yes, exactly. This is very easy in computers. Dividing by 2 and multiplying, you just make a shift left or shift right operation. And even in the odd case, the shift right, you just but you still need to save these remaining things in the odd case, but you can do that. So multiplying by 2 and dividing by 2 is very efficient in hardware implementations. So this becomes important in computers, okay? This method leads to very fast hardware implementations since doubling and halving means half and dividing it by 2 of binary numbers can be performed using binary shifts. Okay, so let's take a break and we will continue with variable size decrease algorithms. Okay, let's take a 10-minute break. Okay, screen sharing is still on, I think. So let's continue. Now we will continue with the variable size decrease algorithms. Sınıf başladı arkadaşlar ders. Variable size decrease algorithms. Sana atamadım. Variable size decrease algorithms. In here, I will just give a very small description and example. The size reduction pattern varies from one iteration to another. Example, Euclid's algorithm for computing greatest common divisor. Okay. So computing a median and the selection problem, because we talked about Euclid's algorithm is n mod m is something something. I already given that. So this is the variable size reduction pattern. It's the same thing. So computing a median and the selection problem. Okay. So what is the selection problem? Let me give the description first. Finding the kth smallest element in a list of n numbers. Okay. This number is called the kth order statistic. When k is equal to the ceiling of n over 2, this number is called the median. Okay. So the kth smallest number, how would you find it? What's the very easy way that comes to your mind first? The kth smallest. Yes, that's one option. And find minimum, that's the smallest. And then take it out, take the minimum of the others, take it out, okay? So do this like k times. In the k part, the minimum is what you're looking for. That's another option. But these are more like exhaustive search wise. I mean, sorting is okay. You can use intelligent things like quick sort, but still, obviously. But there are other ways of doing this, more clever ways. I mean, sophisticated ways, let's say. Obviously, we can find it by sorting the list. And then finding the kth smallest element. But when sorting the list, we are actually doing too much. We find all K's, like we sort all of them, but we're not interested in the, I mean, I'm just looking for the fourth smallest element, for example. Well, sorting gives me the first, second, third, sixth, seventh smallest element. It gives me a lot of information at the expense of some sort of complexity, of course. But it would be like an overkill, right? Maybe I don't need that much of information. Maybe I can do better than that. I can achieve better complexity because it gives me too much, okay? But wouldn't it be an overkill? Because we don't need the entire list. But just the kth smallest element. What do you mean by insertion sort to the kth element? But with insertion sort, you don't keep, you keep a sorted list, but maybe the kth element will be this, I mean, the kth iteration, let's say, maybe it will be the minimum of the beginnings. You don't know where it will go in the previously sorted list. Okay, I mean, you may be in the kth step, but it may turn out that the element that you're taking care of at that time is the smallest of the list. So it's not like that. Can we do better? Hint, think of quick sort wise, but don't do sorting. So that's why the algorithm will be called quick select, not quick sort. But in quick sort, what were we doing? We had a pivot element, right? We know, I mean, irrespective of what our final ultimate goal is, we know that if we have a pivot element, I can group all the elements into two, in which one group is the ones that are less than or equal to that pivot element, and the other ones are greater than or equal to that pivot element. And I know that I can do this in linear time. I know this from quicksort, okay? In quicksort, I utilize this eventually to sort out the entire array, but that partitioning phase. But here, let's say that we also have the partitioning phase, but I don't use this to sort out the entire array. But what will partitioning give me as a result? Let's think about that first. Partition, I mean, can I then use this to find the kth smallest element? Partitioning a given list around some value p. Means that rearrangement of the elements such that left part contains elements less than or equal to p. P is the pivot element. Right part contains elements greater than p. Okay? So I have a pivot element p, the element. I have a left part that is less than or equal to, and that is greater than p. Okay? So, and remember my goal. I'm trying to find the kth smallest element. Okay. If, question to you here, it turns out that it may not always be the case, that there are k minus 1 elements. If that is the case, if it turns out that, then what does this mean? I have randomly selected a pivot, okay, and I partitioned the list into two, the ones that are less than or equal to that pivot element. I mean, pivot element was in the list. I mean, I just randomly selected an element from the list and partitioned the list into two groups, the ones that are less than or equal to that, but they are not sorted within each other, okay? They are just the elements that are less than or equal to P, and the ones that are greater than P. And it may be anything. Maybe I'm looking for the fifth element and fifth smallest element, but this list only have one or two elements, maybe. I don't know that, but I'm just asking you, imagine the case where, luckily, I'm saying, it turns out that there are exactly k minus 1 elements that are less than or equal to the pivot element. And my goal was to find the kth smallest element. Then what do I do? What does this mean? Yes, pivot is what I'm looking for then, right? If there are k minus 1 elements that are less than or equal to pivot, then this is the kth smallest element, right? And with only one partitioned operation, I found it. And I didn't do any sorting, I found it. Did everybody understand? Let's say that, okay, maybe in an example, I can say, let's say that my pivot is 8. That's the element. And the ones that are less than or equal to that. And I'm looking for the fifth smallest element in this list, okay? And I partitioned the list. Okay, let's say that I have like 2, 7, 10, 5. Okay, let's say that this is my list. And I randomly selected a pivot as 8. And this is my pivot. And the ones that are less than that are what? 2, 4, 5, 7, right? This will be in less than or equal to P part, and 9 and 10 will be in the greater than P part, right? And I was looking for the kth, the fifth smallest element. So there were already 4 elements here. I don't know whether they are sorted or not. They may not be sorted, but then definitely 8 turns out to be my smallest element. But this is only one case. And there may be little less number of elements in the less than or equal to P case or greater than that. But then can I do my search? I mean, if it turns out that what I'm looking for, but I can certainly decide whether what I'm looking for is the pivot element or not, right? I can just look at the size of the elements in this left part that are less than or equal to, if it is exactly equal to k minus 1, then I can say that pivot is what I'm looking for, okay? If not, then I can decide to continue. I'm in searching, remember. I don't want to sort the entire list. I'm just looking for a specific element, which is the kth smallest element. So if there are more elements here than k minus 1, okay, if there are at least k elements here in this left list, can you see? No. Then I know that what I'm looking for has to be here, right? These are irrelevant then. Or the reverse. If the big part is here, then I need to keep looking for in the right list. But of course, changing now it won't be the kth smallest element anymore. It would be n minus k something smallest element. Okay. So I will continue searching in one of these two sublists, according to the results, and I can continue doing this recursively. But this time I'm not doing sorting, I'm just doing searching recursively, okay? By dividing it and the list into two. But first, before moving on to the, probably maybe tomorrow we will talk about the pseudocode for the algorithm that I just mentioned is roughly quick select. But maybe before moving on to that, I will talk about another partitioning algorithm called Lomuto partitioning. And we've seen it in quick sort, a version of partitioning, but it's a little bit of different than the partitioning algorithm we've seen in quick sort, but all of them are linear time. It doesn't matter really how you do the partitioning. The end result is the same. This one is called Lomuto partitioning, okay? I divided into three continuous segments. A segment with elements known to be smaller than p, a segment with elements known to be greater than or equal to p, and a segment that I haven't decided yet, okay? That's the one that I will keep operating on, like in insertion sort, right? I had a previously sorted one, and there was a yet to be processed part here also. So the segments can be empty at any given time. And in the beginning, the first two segments are obviously empty and the entire list is yet to be processed, okay? The segments can be empty. Can be empty, and this is always the case for the two segments before the algorithm starts. So visually describing it, it will be something like this. There is a pivot element here, and the index is L, stands for left, okay? That's the left index. There's the pivot element in the beginning. There's a segment here which is less than P, and it ends with index S. And the second one starts with index S plus 1. It goes on to greater than or equal to P, okay? And this is I, and this is R, stands for right. That's the right index, the rightmost index. And this is the question mark part, which is yet to be processed. So the first segment, a segment with elements known to be, so this is the pivot element, this is the first segment, this is the second segment, this is the third one, okay? And I keep doing it like this, starting with I is equal to L plus 1, the algorithm, the Lomito partitioning algorithm, scans the subarray A left R left to right, maintaining this structure until a partition is achieved. Okay, starting with I here is equal to left plus 1. I maintain this structure until the partitioning is achieved. Okay, on each iteration, compare the first element in the unknown segment I mean, I say this I, but this I changes, okay? In the beginning, because these were empty, they are the same. So compare the first element in the unknown segment pointed to by I by the pivot P. So I compare it with the first element of the unknown segment by the pivot. If AI is greater than or equal to P, if it's greater than or equal to P, then I have to put it in portion 2, okay? So how do I do this? Increment I to expand the segment. I mean, if I increment this 1 further, it was the beginning, it means I have expanded this segment 2 by 1, okay? While shrinking the unprocessed segment. Okay? This is if AI is greater than or equal to P. If AI is less than P, if it's less than P, then I have to put it in, I don't know what's happening, okay, in segment 1, right? If it's less than P. Then how do I do that? The segment with elements less than P needs to be expanded, but this is done by one, incrementing S, the index of the last element. In the first segment. The index of the last element in the first segment, and then swapping AI and AS, and then incrementing I to point of the shrunk unprocessed element. Okay, let me explain this in the previous figure. You may need to keep, I mean, I can't, because this is not the whiteboard, I can't show all of them on one screenshot, so you may need to look into your notes again while I explain this. Now I looked, so what am I doing here? I looked at the unprocessed element, I checked it with the pivot, and I decided that I need to put it in this segment 1, okay? So it means I need to expand this segment 1, and which means shifting all the others greater than or equal to P and the unprocessed ones 1 to the right, okay? So the unprocessed one shrinks by 1, and the segment 1 should expand by 1, and the less than or equal to P, its contents have to remain intact, okay? So how do I do this? My S pointer is the end of the less than this segment 1, S pointer. It's the last index of this segment 1. So I increment it by 1, means because I need to leave room. Sorry. I need to leave room for the new elements. I need to put it here. Okay, so I incremented the index of the last element in this first segment, and then I swap AI and AS. It means I put what I want to put here in this segment, in this part, sorry, in this index, and then what was already in there, I put it here. But this was greater than or equal to P, okay? This is not in the unprocessed segment. So it was in the greater than or equal to P, and it has to remain in the greater than or equal to P. So it was in the segment 2 originally, and it has to remain in segment 2 once I finish this. So how do I do this? I increase this segment by 1, segment 1. I also need to update the end of segment 2 so that it also has this element in it, okay? It's just that its position has changed, but it doesn't matter. It's something that was in segment 2 and it will remain in segment 2. So swapping AI and AS, and then I increment I to point to the new first element. So once I increment I, unprocessed segment, okay, incrementing I to point to the new first element of the shrunk unprocessed element, okay? Is it clear what we're doing here? Now I will write the pseudocode. For example, so my elements are 5, 2, 3, 6, 4, 7, 8, 1. Okay. And this is P. This is S. Continue until 5, 2, 3, 1, 4, and 7 is here. Okay. And that is S. So the pivot is 5. So the pivot will be here. This will be S. So the ones that are greater than the pivot will be here. And then less than or equal to the pivot will be here. I want to achieve this portion, okay? I continue the operation until this is achieved. So any questions about Lomuto partitioning? It's very similar to the partitioning we've seen in quicksort. It achieves the same thing, basically. I can replace what we have seen in quicksort as a partitioning algorithm with this one. It doesn't matter, okay? It's just some partitioning algorithm. The complexity is the same. It's just the details of how the operation is performed with the pointers and indexes, etc., are different, okay? So if there are no questions, I will continue with how can I take advantage of this partitioning to find the kth smallest element in a given list, okay? For the selection, which is called the selection problem. So how can we take advantage of a list partition? Split position of the partition, which means index of the erased elements. Pivot after partitions, okay? Okay. Remember, I explained to you, if S is K minus 1, the indices start from 0, okay? Sk minus 1 means that pivot P is the kth smallest element. Right? You remember why this is true? I'm looking for the kth smallest element, and it turned out that this is the index that is pointing to the pivot P, and indices start from 0. So if S is K minus 1, actually pivot P is the kth smallest element, okay? It doesn't matter whether this portion is sorted each other or not. They are all less than P, okay? So if not, then I will continue in one of these two sublists. But how? If S is greater than strictly K minus 1, greater than K minus 1, then the kth smallest element is what? Then in which part should I continue? Is in which, what can I say? If S is greater than K minus 1, so indices start from 0, S greater than K minus 1 means there are more than K elements in this portion. Part, yes. Again, recursive. So I should continue, I should forget about the rest. I should continue what I'm looking for only in this portion. Can I say that the kth smallest element of this portion is also the kth smallest element of the entire original list? Yes, because this is the smaller part, okay? So the kth smallest is still the kth smallest. So I can continue to find the kth smallest, again, now in this part recursively, okay? Then the kth smallest element is the kth smallest of the left part. Now, if S is less than K minus 1, okay? So I was looking for the fifth smallest element, but now I have like, I don't know, 2 elements maybe on the left, and then 1 element, and then the other part, okay? Then where should I continue my search? Obviously in the other part, right? But now, is it true that the kth smallest of this right part is also the kth smallest of the original list now? No. Now, I should continue in the right part, but I shouldn't be searching for the kth smallest element. I need to update that. The kth smallest of the original is in which order, which xth, whatever smallest in this part? I want something here from 0 to K minus 1, okay? The kth smallest. And I have like some elements here. According to S, maybe. K minus S, exactly. Because S is the index there, and now it will be the K minus S smallest element of the right part, okay? Then the kth smallest element is the K minus S smallest element in the right part. Okay, so I will keep doing this. Maybe depending on the pivot, I may still need to update it in the following recursions, but recursively I will find it. Okay, so this algorithm is called quick select. Renk değişikliğini algılayamıyor. Okay. So let's write the pseudocode for quick select. Okay, I don't want to write the pseudocode for quick select because, okay, let's continue tomorrow. Okay, we are already 5 minutes late because I want to continue with the, I mean, I could have written the pseudocode, but I won't have time to explain. We will analyze its complexity as well, and I want it together with the pseudocode. Okay, once you do the pseudocode. See you tomorrow. Take care of yourself, physically and emotionally.